Okay, this video is going to cover section 18.7, talking about anions of weak acids acting as weak bases. So with that, let's just go ahead and get started. And to get started, we are going to write a strong acid reaction. So let's talk about HCl reacting with H2O. And that's going to dissociate completely to form H3O plus and Cl minus. So when we say it dissociates completely, we say HCl is a strong acid, so we can label these. Let's practice our labeling, acid and base. And that makes the hydronium the conjugate acid, and the chloride is the conjugate base. So when it says it goes to completion or dissociates completely, that means we form H3O plus and Cl minus, and there's no HCl left behind. And that basically also tells us that the reverse reaction just doesn't happen. So this reverse reaction can't happen. And the reason is because chloride is too weak of a base in order to take that proton back from the conjugate acid hydronium. So we can say that the conjugate base of a strong acid is too weak. So it really does nothing. And we can think of this also, if we think about a sodium chloride solution dissociating into water, we'd end up with Na plus and Cl minus. And if we measured the pH would simply be 7. The chloride just isn't strong enough to take away a proton from water. If it did, it would make HCl, which is strong, and would just redissociate back into H3O plus or back into water and chloride. So this chloride is just too weak of a conjugate base in order to do this. So the conjugate base of a strong acid is too weak, it does nothing. So let's talk about weak acids now. Let's talk about HF, hydrogen fluoride, or hydrofluoric acid. Reacting in water, we know this is a weak acid. It's not one of the strong ones we had to memorize. And we end up with a H3O plus solution and F minus. So again, let's practice labeling these. These are our acid, this is our base. And we have our conjugate acid, and fluoride is our conjugate base. Now, because this is weak, we know that the reverse reaction does happen. That's why it's an equilibrium. In fact, it favors the reactants. This is a fairly weak acid. Well, it's a stronger weak acid, but it just really means that at the end of all of this, once we've reached equilibrium, there's still a lot of the HF around. So it's still going to be primarily HF. That means any F minus that we form, and again, dynamic equilibrium means it goes forward and backwards at the same rate. So that F minus can take away a proton from the H3O plus to form the original reactants. So we can conclude that the conjugate base of a weak acid is strong enough, but still weak. So that is to say, that is to say fluoride can act as a weak base. So we can think of sodium fluoride, that's where that came from. A sodium fluoride solution is basic. And we can prove that if we look at just F minus by itself. So if we were to take some F minus, so this would be A, this would be B. If we were to just look at F minus and dissociate this into water, what we end up with is the fluoride is going to take a proton from the water molecule, or the other way of saying that is that water is going to donate a proton to the fluoride ion, and we're going to end up with our weak acid, HF, and hydroxide. So again, practicing our labeling, we're saying that F minus is a conjugate base in the last reaction, so we kind of know it's going to be a base, but we also know it's a base because it's accepting a proton in this reaction. So this is a base, which means water, in this case, is acting as the acid. And so we've talked about this before, where water can be both an acid and a base. We called it amphoteric. That's the word for it. And we can see here that now fluoride is the base, water is the acid. So that makes this the conjugate acid, which we know is an acid. And then we have the conjugate base, which in this case happens to be strong. So because that hydroxide is present, the pH of the solution goes up and it would be basic. So let's see how this all ties in together. If we were to talk about the Ka of HF, so Ka again means the acid equilibrium, Ka of HF is 6.8 times 10 to the negative fourth. But we can't use that Ka for the previous reaction 2B because it's talking about a base reaction. So we need Kb for F minus. Well, how can we get that? What we can do is we can write out what each one of these is. So for the equilibrium reaction Ka of HF, that's reaction 2A. Ka is going to be concentration of products over reactants. In this case, our products are H3O plus and F minus, and our reactant was HF. And for Kb, that's reaction 2B. Again, it's products over reactants. Our products is HF and OH minus, and the reactant was F minus. Now, if we take these two and multiply them together, bear with me. So I'm just going to take and move that up there. Now I'm going to multiply the Ka times the Kb. Let's move this down here and make it really clear. So now we're multiplying Ka times Kb. What do we get? Well, we can cancel out the F minus, we can cancel out the HF, and then the only things that are left over are H3O plus and OH minus, which we know what this is. This is the autoionization of water, gives us Kw. So we can conclude now that Ka times Kb is equal to Kw. And if we were to take the negative log of all of these things, since Kw is always 1 times 10 to the negative 14th, negative log of that is 14, and we can also say pKa plus pKb is equal to 14. So either way, if you have a pKa, you can find the pKb. If you have a Ka, you can find Kb. If you have Kb, you can find Ka, so on and so forth. So in this case, we have Ka. We know the Ka for fluoride, or for hydrofluoric acid, is 6.8 times 10 to the negative fourth. So Kb for the fluoride is simply going to be 1 times 10 to the negative 14th divided by 6.8 times 10 to the negative fourth, which should give you 1.5 times 10 to the negative 11th. So now we've got Kb. Now we can come up with a theoretical reaction and figure out what the pH of a fluoride solution would be. So let's say, as an example, just kind of making this up, what is the pH of a 1 molar sodium fluoride solution? And sodium fluoride, you may recognize that if you go look at your toothpaste. If you have an anti-cavity toothpaste, this is the chemical that aids in that. It's actually the fluoride ion will kind of catalyze or takes part in the reaction that's called the recalcification reaction, in which helps your body add calcium back into your tooth enamel via a phosphorus reaction. So you can look that up if you'd like in your spare time for fun. But the sodium fluoride is what takes part. That's why we add fluoride to toothpaste. That's why fluoride is in drinking water. So we have to take precautions when we add that fluoride in to make sure it's not throwing the pH too far out of balance. So if we write this reaction, sodium fluoride can dissociate into Na plus and F minus. Well, the sodium's not going to do anything, so let's take that down and use the F minus. Fluoride plus water dissociates to form hydrofluoric acid and hydroxide. So here's our Rice table. Our initial concentration, well, let's get fancy here, we can. Our initial concentration of the fluoride was 1 molar. So we said this is 1 molar. And we're not going to worry about water. That's 0. That's basically 0. So we're going to lose some from here, and we're going to gain it onto the right side. And again, this should become pretty automatic by now. And then we come over and write what's KB. KB is products over reactants. We know this already, but let's just write it just for making sure we're understanding everything and getting the practice. Practice makes perfect. What we end up with is, of course, x squared, so x times x, so I'll just kind of shorten that into x squared, too short, and 1 minus x. And again, we're going to assume x is small. Now what I haven't been doing is using the 5% rule to check. You should always do that. But in all of these cases, we've kind of designed these experiments and these reactions to know that x is going to be small, and less than 5%. We know KB is equal to a number. We just calculated that in the previous step. That's 1.5 times 10 to the negative 11th is equal to x squared over 1. So really, we just have to take the square root of both sides. And really quickly into the calculator, 1.5 to the negative 11th. And taking the square root of that, I get x is equal to 3.87 times 10 to the negative 6th. And again, remember that x in this case is equal to the concentration of hydroxide. It's also equal to the concentration of HF, but that's not the part we're interested in. I want to know the pH of this solution. So remember, there are two ways to do this. You can either calculate the pOH and convert that using the pOH plus pH is equal to 14, or, or we can convert from hydroxide into hydronium. Let's do that one. So my concentration of hydroxide was 3.87 times 10 to the negative 6th. I know that Kw, 1 times 10 to the negative 14th, is equal to the concentration of hydroxide times the concentration of H3O+. So to get the concentration of H3O+, is simply 1 times 10 to the negative 14th divided by our concentration of hydroxide, 3.87 times 10 to the negative 6. And again, running to the calculator really quickly, I get the concentration of hydronium is 2.58 times 10 to the negative, 2.58 times 10 to the negative 9th. And now I can take the negative log of that. Remember, pH is equal to negative log of the concentration of hydronium. So we have pH is equal to negative log of 2.58 times 10 to the negative 9th. And again, I'll just type this into the calculator really quickly. And I get a pH equal to 8.6 with sig figs and rounding. And let's just double check to make sure that makes sense. We said that because of the fluoride solution, it's acting as a weak base, so it's going to make the solution basic. It should be greater than 7, between 7 and 14. 8.6 is definitely greater than 7. And sure enough, this solution is basic. So that's doing a problem showing how the conjugate base of a weak acid also acts as a weak base. So when we isolate that weak base, and that's kind of the important part of this, is that we're taking that weak base and we're just putting it by itself. I didn't start with a solution of hydrofluoric acid down here because that would be acidic. I had to start with a solution of just the anion from our weak acid. So the anion of the weak acid is a weak base, and from there we can calculate that the solution would be basic.